Hello everyone. In this video I will be solving GATE 2020 chemistry question number 18. They state that the maximum number of microstate for D2 electronic configuration is. Before solving directly the number of microstate for D2 electronic configuration, I would like you to introduce the concept of microstate, how it emerges and the reason. So let's have a look on the concept of microstate. So this comes from the optical absorption spectra, uh, also known as the electronic spectra of the coordination compound. I take the example of hexa-aqua nickel 2 plus complex ion. It is a octahedral D8 complex ion. So according to ligand field theory, the metal d orbital in an octahedral field T2G and EG, and so that in for this complex there are 6 electron in T2G and 2 electron in EG. So LFT predict that the number of electronic transition will be 1, but we find that the absorption spectra is way more complex than the expected. So instead of a single absorption band, we get multiple absorption band. So here LFT is unable to explain this. So the key points here are that the LFT from ligand field theory, we expected only one absorption band, that is one electronic transition, but through experiment we get 3 absorption band, and the reason behind this was that the LFT assumes that there is no electron-electron interaction. However, this cannot be possible as the electrons in d orbitals have repulsive interaction, and hence it affects the energy overall. So what happens when the electron-electron interact? So let's again take one simple example of D2 ion in octahedral ligand field. So we can take a lot of example. For example, this I am here it is shown for excited state for the same D2 ion, but when it was in ground state, these two electrons can be in any two orbital of T2G, for example XY and XZ, or it can be in XZ or YZ, or in XY and YZ. So there are again number of microstate possible in ground state itself, but let's just discuss one excited state example. So if I am saying that in ground state my two electrons were in XY and XZ, so in excited state, the transition from T2G to EG can happen in two different manner. For example, my XY electron goes from T2G to Z2. Okay, and for the same transition, uh, uh, my instead of my XY DXY electron, my D XZ electron jumps from T2G to EG of EZ2. Okay, so there are in total I have only depicted two microstate with different energy for the excited state, for one of the excited state, we can say. So now, according to ligand field theory, it says that both the excited microstate have the same energy. But however, this is not the fact. The fact is that these two microstate corresponding to the excited state have different energy. And this we can actually simply understand by understanding the orbital associated with these microstate and filling up their electronic density. So for example, if I choose microstate 1. So the electron density will be such that, yeah, so this dz square, okay, sorry, yeah, and for green, for T2G, it is in xz plane, so xz is this plane, okay, so this orbital will be filled. So this is how my electron density looks like for microstate 1. And again for microstate 2, and the T2G xy. So xy plane, yeah, this. So this orbital dxy will be filled. I mean the electron density here. So you can just see that these two microstate 1 and 2 have very different electron density, and therefore these two different microstate have different energy because the electrons in d z square and d either xz or xy, they interact very differently here. So So the complex that will observe depict these transition will absorb different wavelength of lights, and this is actually contrast to what ligand field theory predicts. So to find out the total number of absorption bands, we have to predict the total possible microstate for the D2 ion configuration, for example that we have taken. So here a group of microstate, actually I can just write here. So a group of microstates with the same energy is called a term, and the number of electronic transitions can be predicted from the number of terms. Okay, so yes, coming to the what this electron-electron transitions gives us, that the quantum number, which determine how the electrons interact. So the energy of the microstate depend on these quantum number, for which are ml and ms of each electron. This is called the Russell-Saunders coupling of electrons. So what are ml and ms? So ml is the magnetic quantum number of a single electron, and it goes from minus L to plus L. And capital ml is the total orbital angular momentum for total number of electrons. So this is, we can actually calculate as the sum of magnetic quantum number of single electron. And the maximum total orbital angular momentum ml, capital ML value, is actually correspond to the quantum number capital L. And this capital L is the total orbital angular momentum quantum number. So this is the quantum number associated to ml. And the microstate in terms due to the angular momentum, we can just write it as 2L plus 1. Okay. The quantum number capital L that we have seen alone does not define the term. So in addition, we must also consider the interaction of the spin of the electrons. For that, ms is the spin quantum number of a single electron, and the capital Ms is the total spin angular momentum. So it can be calculated as the summation of spin quantum number of each electron. And the maximum ms value is equal to the quantum number associated with it, which is capital S. And this quantum number is the total spin angular momentum quantum number. And the microstate in the term due to spin is simply 2s plus 1. Overall, the microstate from L and capital S, we can write it as the product. So it is product of 2L plus 1 and 2S plus 1. Now, to calculate the microstate for free D2 ion, for D2, this D orbital here, you can see just the depiction. So we just have to first obtain the total angular quantum number and total spin quantum number. Okay, so we need to find out ml and ms and then the corresponding quantum number, that is capital N and capital S. So that is here is that ml for D2 is simply the summation of ml I, which is ml1 plus ml2, and this ml1 and ml2 can have actually the value from plus 2 to minus 2 and ml2 again plus 2 to minus 2. So for ml just a summation, so it will also goes from plus 4 to minus 4. So the maximum value of ml is plus 4. So my L is actually 4 here, correct? And the ms is the summation of ms1 msi, which is ms1 plus ms2, and this can have the value from plus half to minus half, so that my ms become my total spin quantum number is plus 1, because it is the maximum of ms. So my s is plus 1 and my ms goes from plus 1 to minus 1. So the microstate for a free D2 ion, so the possible microstate and the overall number of microstate for a free ion with D2 electronic configuration. So we can express it in a microstate table. So here you can simply just do ml slash ms. So your number of or vice versa. So you can just define your table by yourself. So here to define the columns I am using ml, and to define the rows I am using ms. So for D2 we have ml going from plus 4 to minus 4, and ms from minus 1 to plus 1. And so it is simple, just here the possible number of microstate corresponding to ml minus 4 and ms minus 1. It is actually not possible due to Pauli's exclusion principle, and this is that ms value minus 1, meaning my ms1 plus ms2 should be minus 1. That is, both of them should be of same spin, minus half and minus half. Also, my minus 4. So this my minus 4 gives me the ml value minus 4 here. So this just two electron cannot be in the same orbital with the same spin. This it cannot disobey Pauli's principle. So therefore here there are zero microstate, and similarly zero microstate not possible in this column, this space of ml value plus 4 and ms value minus 1, and same with the ms plus 1. We have not no, microstate not possible here too. And the other space, for example here the ml value, which so here the l value, you can see that ml1 is for example 2. So my ml2 is minus 1 here. So both of them can have the summation of minus 2 plus minus 1 giving me minus 3, and with the spin of minus half each, so that they are following Pauli's principle, and therefore there are number of microstate is actually 2 1, sorry. Yeah, so again similarly if we go on filling these, so you can see that the maximum number of microstate is in where ml is equal to 0 and ms equal to 0. So there are a total of 1, 2, 3, 4, 5 set of microstates, making 5 terms. Okay. So in total there are we get a overall number of microstate in this table. We arrive at the number of 45. So for D2 we get a total of 45 number of microstate. So this goes with the formula number of microstate n factorial n minus r whole factorial r factorial, where n is the total number of electron orbital can accommodate. So for the case D2, my total number of electron that d orbital can accommodate is 10. So it becomes 10 factorial upon 10 minus number of electron. R is just the given number of electrons. So it's 2 whole factorial and 2 factorial. So this will give me the value 45. For this formula, this is actually the number of microstate. This is based on the term symbol that we are given, because as D2 have a total of 5 terms. So term symbols. So for each term symbol, we can find the number of microstate associated with it using this. And for all those 5, if we sum all these up, then we get a total of 45 again. So for reference, you can check out the book Coordination Chemistry by Ajay Kumar, and for NPTEL reference, you can check the video lecture from NPTEL, Optical Spectra by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link for it. Thank you.